Hey all, and welcome back. Another round of vectors here. And this video we're going to be talking about the cross product. So now 2 videos ago we were talking about a scalar multiplication with a vector and how it stretches or shrinks the length of the vector but keeps the direction the same. And then last video we were talking about the dot product, namely we find the 2 vectors, we take the 2 vectors, we find the pieces that are parallel to each other and then multiply those. And the output is a scalar. Here is a third way of actually multiplying vectors called the cross product. And the first thing that we should note how this differs is that we get a vector output. Vector resultant, I guess I should say. Resultant. In other words, once you perform the cross product, you end up with a vector. So in that sense, it's somewhat like that scalar multiplication. But differently, the difference here is that the resultant vector r is always going to be perpendicular to both a and b. In other words, you use the cross product between a and b, and your resultant vector r will be perpendicular to both of those vectors. And we can go through and actually see how that is in a particular example if we're using numbers. So that being said, let's get at this. And the first thing that I'm going to actually talk about is what's called the right-hand rule. The right-hand rule. And most of the time, since that takes too much, most of the time you'll actually see me abbreviate it RHR, right-hand rule. And this is just a rule of thumb for keeping the directions consistent. Now, we could go into all the math, we could go into a bunch of other stuff, but essentially what you need to know in order to do this is that all coordinate systems are right-handed. So coordinate systems, are, I'll put right-handed. Okay. In other words, let's take a look here. If I actually start with a coordinate system, say this is my x direction and this is my y direction. So if this is y and this is x, there is only one direction that z can be. And we have to use the right hand, we can use the right hand rule to actually figure out which way that is. And actually if x is to the right and y is up, that means that z will actually be out of the board. Okay. Now if we had chosen some sort of different orientation, say for example, that we chose x to be up and y to be the horizontal axis. So, excuse me. If we chose x to be up and y to be the horizontal axis, then all of a sudden z will not be out of the screen, but rather it will be into the screen. Okay. You say, well, how do I do that so quickly? Let's talk about the right-hand rule. And actually, I'm going to actually use the video camera here. So the idea is, for the right-hand rule, the vector that comes in the first position is always what we'll represent with our fingers. So with your fingers, point in the direction of the first vector. Okay? So something like this. Then the next thing is that we take our palm and we actually turn our palm in the direction of the second vector. So for the case that's on the screen right now, let's put our fingers pointing up in the x direction. That matches what direction x is. And then we take our palm and we point it in the direction of y. So you notice that my palm is now pointing this way, my fingers are pointing up. And then lastly, my thumb will give the direction of z into the screen, as you can see. Now, I'll of course put an illustration up right there and give you a little bit of practice there. But the idea is that's what dictates our coordinate system, how we set up our coordinate system. You say, why do we choose the right hand? You had a 50-50. You either choose the right hand or the left hand. In this case, we chose the right hand. If you're familiar with it, this actually makes a difference if you've gotten into chemistry at all. There's something called chirality. Chirality. Something like that. And this actually deals with the handedness of molecules. And it turns out there's actually some diseases that depend on how your protein, if it's a right-handed protein, you're okay, but if it's a left-handed protein, you end up being sick. So that's just basic right-hand rule. So again, practice for yourself. If x is in the horizontal direction and y is up, Try practicing your right hand rule. Point your fingers in the direction of X, point your palm in the direction of Y. You'll end up seeing that your thumb is actually pointing out of the board or out of the screen. So, and of course, the last thing that you should do solemnly swear, I do solemnly swear to use my right hand. We'll get more practice, but this is just an introduction. Do solemnly swear, use your right hand. And you say, okay, well, that's not too hard. I'll tell you right now, the people that mess this up the most are right-handed. And the reason is this: you're so busy working on your homework, you got your pencil in your right hand, you're scribbling away, and you use your left hand, the hand that's available, to actually perform the right hand rule. So those of you that are right-handed, please be careful. You're going to mess this up at some point. Put a big X on your hand if you have to, but don't mess this up. It's really important. So that's the basic right hand rule, and I'll say most coordinate systems, or at least all of them that you'll see in physics, are going to be right-handed. So let's go ahead and clear that off. So that's the first thing, and hopefully you'll see how that comes in a few minutes. So the first thing, just the dot product, as we've previously discussed, is based on finding the components that are parallel to each other and then multiplying them. Here, the cross product is actually going to find the components that are perpendicular to one another and then multiply them. So the idea comes up like this. Let's get a couple of vectors. Let's say, hey, here's vector A. Ooh, hot orange. Oh, excuse me, I forgot to change the colors. Well, hot orange it is. So there's vector B, and here is vector A. So just like previously with the dot product, let's slide B until it's tail to tail with A. There we go. And now what we're going to do is same song and dance. Let's drop a perpendicular from the tip of B to A. And I'll make that, let's make it a different color. We'll make it blue so that you can see it. So in the past, we called this distance, we called that distance B parallel. And what we're going to call this distance right here, this would be B perpendicular. So now the cross product, what the cross product does is it finds the component perpendicular, or the perpendicular components, and multiplies them. So if we're dealing with this, we see that perpendicular component B perpendicular times A. That's what the cross product's going to give us. So if I actually think about my trig functions, we can see that this would just be, I'll keep the magnitude of A. I'm just swapping the order because I like them alphabetically for some reason. And here, the perpendicular component, we would use the sign. And we're done. Well, almost. Let's go ahead and talk about notation for a moment. So the first thing is notation-wise, is we still have to keep our vectors. So don't forget, we need A and B, and they're both, we keep our vector notation. And in the middle, instead of putting a dot for the dot product, we're going to put a cross for the cross product. The other thing I mentioned previously was that the cross product results in a vector. And right now, as this is written, the left-hand side would be a vector, the right-hand side is a scalar. That's a no-no. We cannot set vectors equal to scalars, even in notation. Like a physicist would look at this and say, that's no good. That doesn't make any sense. It's like saying an apple is equal to an orange. So how we rectify this situation, at least in this case, is that we put a magnitude sign in here. So what this leftmost expression actually gives us is the magnitude of the cross product. Conceptually, it's taking the perpendicular component and multiplying it by A. Now similarly, like last time, you say, wait a minute. Why couldn't I do A perpendicular to B? Why can't I do this instead? And I say, absolutely, go whole hog, let's do that. So let's drop a perpendicular from the tip of A to B. And I guess we'll do this red color. So perpendicular from A to B. And that looks about right. Good. And again, I apologize, I've failed to label that, but this is the angle theta, just like last time. And so if I look at this right triangle right here, this section, this red section, would be the perpendicular component of A to B. And again, you notice that we're still going to use the sine. So even though I have this here, this would just be equal to, again, A, B, sine of theta. And now I'll have to be very careful. Say this is B cross A. We'll see when we do the algebraic manipulation that we actually do get different values, and we'll see how those values compare. But the magnitude is the same. So we're actually, I'll give away right now. If you swap the order, if you do A cross B, if you swap the order and do B cross A, you're going to end up with an additional negative sign. So when you take the magnitude, that disappears. It doesn't care. I mean, if a negative sign, that the magnitude strips that away. So that's why from the graphical standpoint, you end up with the same expression. The magnitude of A times the magnitude of B times sine of the angle. And it doesn't matter. That's why it doesn't matter here. Okay? We'll see from the algebraic standpoint that it does matter. You'll actually get an extra negative sign. So these do not commute, so you have to be careful. It makes a difference which way you go. Now, I mentioned the right-hand rule before. This perhaps this would have been better suited right here. But this is how you do the right-hand rule, is that this, whatever vector is the first vector in your cross product, that's the direction your fingers point. Okay? So it's a positional thing. Fingers always go in the direction of the first vector in the cross product. Your palm points in the direction of the second vector in the cross product. And your thumb is in the direction of the resultant. Okay? So it's very positional. Fingers, first vector, palm, second vector, thumb is in the direction of the resultant vector. Okay? Every time. Your coordinate systems are like this as well. Okay? So let's go ahead and get the algebraic one while we're at it. Okay, so this one is going to be a little bit trickier. Unfortunately, it's not as nice as the dot product. So algebraic. Okay. Now, of course, I could give you the long expression, and at the end I'll write it down just so that you can actually see it and kind of understand where it's coming from. But for the time being, let's go ahead and we'll start off with vector A, which is AX, AY, AZ. And we'll do B, which is BX, BY, and BZ. And just like the dot product, I'm not going to go through the linear algebra or the various mathematical steps that actually tell you how this comes about. Okay, if you're interested, again, come upstairs, we'll crack open the linear algebra textbook, we'll see if we can come up with everything. Okay, it's going to have to do with determinants and some other stuff. So if we actually want to calculate out the quantity, where do we want to go? Let's go here. A cross B. This is what we want to actually calculate out. And notice I'm not using the magnitude signs now, okay? So we'll actually get the direction as well. This is how I do it. And I recommend doing it this way until you're comfortable enough to shortcut it. So what I'm going to do is very algorithmic. I'm going to write a 3x3 matrix, okay? 3 columns, 3 rows. So the first row, I'm just going to put X hat, Y hat, and Z hat. Okay? The second row, I'm going to use my first vector. So I'll do AX, AY, AZ. And my third row is going to be my second vector, BX, BY, BZ. Okay. Now, the next thing I'm going to do is I'm actually going to Oops, let's paste that as well. What I'm going to do is rewrite it, write it a second time. And I'm actually going to set it down right next to it. Okay. This is more for just doing the calculation. Okay. And how the calculation goes. So we're interested in A cross B. I'll say, okay, it's equal to this whole rigmarole, but it's kind of disguised. So let's get an idea about how this goes on. Now the next piece, let's draw diagonal lines, okay, at 45 degrees. So we're going to draw a diagonal. We'll draw a diagonal line, and why don't we go ahead and make sure it's a line. So we're going to draw a diagonal line down through, just like that. And we're going to write down each of the things that that diagonal line goes through. Notice there's always an X, a Y, and a Z. And you'll also notice it's always in alphabetical order. X, Y, Z, X, Y, Z, X, Y, Z. So this first one we'll write down, we've drawn the diagonal, and what we're going to write down is X hat, AY, BZ. That's our first piece of this cross product. Now we rinse, wash, and repeat. Let's do it again, except now we're going to do Y, Z, X. You say, well, that's not an alphabetical order. Say, of course, yeah, it is, right? Just think of it being in a circle. So X, Y, Z, X, Y, Z, X, Y, Z, X, Y, Z, X. So it's still in alphabetical order. So this is our second term, and we'll write in plus Y hat, AZ, BX. And of course you can swap these are the simple multiplication like you've done, so you can swap these around if you prefer. Third one, remember to change the color again. Go Z, AX, BY. And this is why I wrote it through, I repeated it, right? If I'm drawing the diagonal lines, it just helps visually to be able to see that a little bit better. So we have that one. Of course, that would be Z hat AX BY. Now, unfortunately, we're not done yet. Okay, we're halfway done. What we do is 3 diagonal lines, upper left to lower right, alphabetical order, XYZ, YZX, ZXY. Okay. We have 3 more terms. Now it's going to go from the lower left to the upper right. Again, notice that it always has an X, a Y, and a Z, Y, and a Z. Now, that's the first thing. The next thing we have to be careful about is that when we're going from lower left to upper right, doing the cross product, we introduce a negative sign. Excuse me. We introduce a negative sign. So this term would be minus BX, AY, Z hat. Well, we're not done yet. Got to do another one. So we go BY, AZ, X hat. Like that. We have minus BY, AZ, X hat. We do a third one. BZ, AX, Y hat. Minus BZ, AX, Y hat. And now we're done. That is the full-blown cross product. Of course, we can simplify a little bit. If I take the terms with the X hats and put them together, we could do something like, okay, well, this is X hat, AY, BZ, minus AZ, BY. And do the same thing. Y hat would be AZ, BX, minus AX, BZ, plus Z hat, and AX, BY, minus AY, BZ. Oh, excuse me, BX. So even with it in front of me, sometimes I screw it up. Okay? This is the kind of the full-blown expression. Now, again, you can see why I don't like memorizing this piece, just because I'm prone to sometimes swapping around letters. So I tend to memorize. Anytime I do it, you'll catch me doing it this way. I'll actually write out the whole thing and do the diagonal lines and make sure I've got everything all squared away. This is the way I tend to do it. Now that's very algorithmic. This is how you do it. This is what you have to do. And I said, hey, the resultant is actually always perpendicular to that. So why don't we, we'll do something somewhat that I usually don't do. Why don't we go ahead, I'll give you two numbers, I'll give you two vectors, and we'll actually work it out real fast here just in the video, just so that you can have some practice. So let's run an example here. We'll say something like this. I don't know. A is 1, 2, and 3. We'll say B is, I don't know. Let's say 6, 5, and 4. Just grabbing numbers out of thin air. So if you want, here's a moment for you. Go ahead and pause the video here. Okay. I'm gonna go ahead. Let's go ahead and actually figure out what A cross B is. So I'm gonna set up my Y hat, Z hat. Okay. Go ahead and set this up. I said 6, 5, and 4. Okay. I'm going to go ahead and copy this. Like so. Good. And let's go at it. So I'm going to take a line, draw it diagonally down. So we have something like x hat times 2 times 4. And the next one, y hat, we have plus, so remember right now we're doing pluses because we're drawing it downwards. Hat 3, 6, and let's go again, z hat 1 and 5, plus z hat times 1 times 5. Like I said, we're only halfway done now. Right, we've gotten the positive values, now we got to get the other ones, the lower left to upper right. So we draw this one, we have something like minus, very important, 6 times 2 times z hat minus 5 times 3 times x hat minus 4 times 1 y hat. And now we have our final answer. Of course, we want to simplify this a little bit more. Let's go ahead. So we have 8x minus 15. So we have a minus 7 x hat. We have 18 minus 4, so we have plus 14 y hat. We have 5 minus 12. Got to think about that for a second. Minus 7 z hat. This is our result. A cross B is equal to this rigmarole. Notice it's a vector. That's the first thing, and it's actually in 3D. Right, I gave you a couple 3D vectors. You got some thing that's in space somehow, but frankly, I think it's hard to visualize. I've got my A vector in space some direction. I've got my B vector in space in some direction. I do the cross product, wham, this is a third vector. Now, the one thing, that's the first thing. Now, you say, okay, well, I did this process. Greg told me that this is the resultant. But one thing that I also told you is that the resultant is always, 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 so I'll call this the resultant R. The resultant R, if you've done this correctly, will be perpendicular both to vector A, and R will be perpendicular to vector B. So let's go through and let's find that out. Let's show that that's actually true. Let's show that R is perpendicular to A and that R is actually perpendicular to B. So let's go through and check this. So the question we have is, how can we check if two vectors are perpendicular to each other? And this you might not realize, but this goes back to the last lecture. We talked about the dot product takes the two components that are parallel to one another and multiplies them. So what should we get if two vectors are perpendicular? We should get 0. If R is truly perpendicular to A, one way to check this is, let's see what value we get when we take R dot A is equal to 0. Question mark. Let's check this. If R dot A is equal to 0, that shows that the two are perpendicular. Let's go ahead. It's a good dot product practice. 7, 14, negative 7. Dot 1, 2, 3. Of course, they could have done it the opposite way. The dot product is cumulative. So put equals 0. Question mark. Well, dot product, 7 times 1, that would be negative 7, plus 2 times 14, that's 28, minus 7 times 3, that's 21, equals 0. And we say, ho-ho! Howdy, howdy! And if you want to be really fancy, you put something like QED. That's Latin for booyah! No, it's some Latin phrase, so that's what, I don't know. Something like, which was meant to be shown. Okay? So this shows us that R is indeed perpendicular to A. Of course, I also said that R should be perpendicular to B. So we go and check. Is R dot B equal to 0? You get, so you can, of course, you could probably do this faster than I can. Right? You guys are a lot faster at this kind of stuff. 6, 5, 4. Question mark, 0. And this one looks a little more intimidating, right? We got negative 42. And 14 times 5, well, that's 50 plus 20, so that's 70. Plus 70. And then 4 times negative 28 equals question mark 0. And indeed, let's see, 28, 52, 7, 0. Yes. Haha, victory. Now, if you get tired of writing QED, you can also do just a square. So like, you drop that on a math professor or, another physics professor. So indeed, R is both perpendicular to A and B. The cross product has worked out. The algebra had worked out fine. Cool. So the other thing that we should take a look at, let's go ahead and get rid of this, is I already warned you what happens if we flip the order. So instead of doing A cross B, what's our result if we do B cross A? What do we get here? So I'll let you go at it. You can pause and feel free to resume whenever you want. But I am going to go through this now. B is in the first position. It goes in the second row. So now I have 6, 5, and 4. A is in the second position, so it goes in the bottom row. 1, 2, 3. Let's go ahead and, let's go ahead and copy that sucker and drop it in. And let's go at it. Let's draw our pretty lines. Pretty. So I get something that says, okay. In fact, let me just draw all three. Well, yeah, I'll do it. X hat times 15. And now you probably don't even have to draw the lines in anymore, although I would encourage you to if you're prone to swapping numbers. Here's 4 times y hat. There's 12 plus 12 z hat. And we'll go to that ugly red color. Ugh. And we see the same thing. Don't forget your minus sign. Minus 5z hat minus 8x hat. So we draw in our last line and we have a minus 18y hat. So at the end of the day, when we mix it all together, we get something like 15 minus 8, that's 7x hat. We get 4 plus negative 18, that's negative 14 y hat. And we have 12 and minus 5, so that gives us plus 7 z hat. And so again, well, we see the same numbers across A. There we go. So we see that what happens is A cross B is equal to the negative of B cross A. If I compare this result that I just got, B cross A, sorry, I thought I had a square selected there. If I compare that to what I had previously right here, you see that those are negatives of each other. If I put a negative sign in front of this expression, I will end up with the original resultant. So it turns out if I swap the order in the cross product, I end up with an additional negative sign. So pretty cool. Be careful about that. I think that's where we're going to end for right now. I say thank you for your attention. Again, if you're curious, or if you say, okay, I want some more practice, pick 6 numbers out of the air, create 2 vectors, and go ahead and start practicing the cross product.